The next step is to filter out the desired signal in the presence of other in-band signals, and this will be achieved with the help of a process called channel selection. And this channel selection can be performed in two ways. Okay, so one way is we can just use the ADC to digitize entire channel and then do the channel selection in the digital domain with the help of digital filters. Or what we can do is we can first filter out the required channel and then we feed it to an ADC. Okay, so in the next few slides, we are going to look at what are the advantage and disadvantage of these two approaches and how to solve them. So now we are going to look at channel selection. The way we are showing, we can perform the channel selection either in the digital domain by digitizing entire band and then performing digital filtering. Okay. Analog domain, where selecting desired channel the help of analog filter before digitizing. So we are going to look at the two approaches of analog and digital domain channel selection. And to be able to understand how it is performed, first we have to understand a bit more details about how an ADC digitizes a signal. Okay. So if you look at the ADC, let's say it is taking an analog input B in, generating a digital output D out. There is another clock input which is always present in an ADC. This clock input tells the ADC at what time instance input signal needs to be sampled, and then later on it is going to be quantized. So this clock signal is always a periodic signal. So inside an ADC, two steps are going to take place. First step is sampling. Once we have taken a sample of input with the help of a clock signal, next step is to quantize, as we have already seen earlier, based on the value of the input voltage, we can assign it one of the predefined bins of an ADC. So this process is also called as quantization. So this quantizer is going to generate this final digital output. Okay, so when we are talking about digitizing the signal with the help of ADC, we also need to ensure that there is no loss of information. And at least for our discussion about the channel selection, we will assume that there is no loss of information because of quantization, just assuming that we have sufficient resolution in the ADC. So we will focus mainly on the sampling aspect, and we need to make sure as a result of this sampling operation, there is no loss of information. So if we look at this sampling operation, let's say we have input V in changing with time. So when we say we are going to perform sampling, it means that we are going to take periodic samples of this continuous time signal. So we are going to, for example, take a sample at t equal to 0, then at some time instant ts, 2ts, and so on. So when we are taking the samples of the signal, we need to also ensure that there is no loss of information. So instead of taking the continuous signal, now we are taking only few of the samples. First, let us understand how we can represent this sampling operation. The sampling operation looks like as if this input signal is being multiplied with an impulse train, which has this impulse in the time domain appearing at this specific time instance. So this sampling operation can be written in the time domain as V in t being multiplied with the impulse train P of t, which gives rise to the input signal samples at time instance and ts. Okay, let's call this signal as V in dash of t. Okay, so now this V in dash of t is going to only have these impulses which are spaced at time instance, which are spaced at ts. And to be able to understand how the signal looks in the frequency domain, we can take Fourier transform of this. Going to be Fourier transform of V in of t into P of t is nothing but convolution of Fourier transform of V in and P of t. So here we are showing the frequency spectrum of input signal first, top side. Here we are assuming that the signal which we are going to sample has this kind of frequency spectrum, this double-sided frequency spectrum around Fc. It has this asymmetry, which is in general possible for complex modulated signals. And on the lower side, we are showing the frequency spectrum of P of t. So as we know, P of t is an impulse train in the time domain. From our signal systems understanding, we know that the frequency spectrum of P of t will also be a impulse train, but with a spacing of Fs. Now, if the two signals are convolving in the frequency domain, here we are going to see how convolution helps in the frequency translation of input signal. So this is the input signal, and here are the impulse train in the frequency domain of the P of t. Okay, so while doing the convolution, we all know that we'll take this impulse train, we can flip, and once we have flipped around the y-axis, we can just move it around. So as we move on the right side, we can see that it is the third, from here, the third impulse, which is at plus 2 Fs, is going to bring down the frequency of input signal, which is around Fc. And similarly, when we move on the left side, the impulse train, the impulse which is at minus 2 Fs is going to bring down the frequency of input signal, which is centered around minus Fc. So as to put it together, let me just show you. These two together are going to bring the input signal frequency to close to DC. And similarly, these two components are going to create this frequency spectrum after sampling. This is at Fs, this is at 2Fs, this is minus Fs, this is at minus 2Fs, minus 3Fs, okay, and so on. And here we have carefully chosen the signal bandwidth to be half of the sampling frequency. So this spacing between these impulses is Fs, this is Fs, and we have chosen this bandwidth B to be equal to Fs by 2. So if we just proceed with the same convolution steps, and we take this impulse train and move further to the right side, further and or further to the left side, we are going to obtain many more replicas of input signal being translated to a different frequency. So if these replicas don't overlap with each other, then if we take these samples and further process, there won't be any loss of information. And this overlapping is also called as aliasing. So we need to make sure while sampling process, there is no aliasing. Resulting aliasing is the overlapping of these replicas. And in this figure, we can easily see that if we just take this frequency translated version around DC, this contains complete information of the input signal. So, in this carefully chosen example, where Fs was twice of the bandwidth and one of the impulse of P of t is aligned with the lower side of the input signal spectrum. We saw that we got this replica which are just touching each other but not overlapping. So the conclusion is sampling operation can actually help us in doing the frequency translation without losing any of information as long as we choose the sampling frequency appropriately. Just to illustrate this point, let me take an example. Let's take an example of Wi-Fi signal at this ISM band around 2.45 gigahertz. And this signal spans, let's take a simple round number of 100 megahertz. Okay, so it starts from 2.4. This band stops at 2.5 gigahertz. So for this is also your ISM band. You will find that Bluetooth, Wi-Fi, Zigbee, and many such applications are present. This band. This band is not licensed, so it is possible to operate in this band without taking a special permission from the government body. Now, if we want to sample this signal without losing any information, we have multiple choices. Okay, one other choice which we saw in the earlier case, but for choice of Fs, which is the sampling frequency, should be such that Fs is greater than 2b, where b is the bandwidth. In our case, it is 100 megahertz. Secondly, we can plan to choose Fs in such a way that, let's say, one of the harmonic in the frequency domain of the P of t aligns with the lower side edge of the desired signal. Because if that happens, then we get this replica which is also aligned with the DC. So this is first criteria. Second criteria we can choose such that this frequency, which is also Fc minus b by 2, is equal to some integer multiple of the Fs. And we can get multiple of choice of Fs which are going to follow these two criteria. So as to simplify the overall design of the ADC, we can choose the lowest Fs which can meet both of these criteria. And for our example, we can easily see that our bandwidth is 100 megahertz, so Fs should be greater than 200 megahertz, as well as Fs should be equal to 2.45 giga minus 50 mega divided by some integer m, which is megahertz divided by m. This is megahertz. And if we just look at the limiting case, we can easily see that by choosing m to be equal to 12, we can get an Fs which is equal to 200 megahertz, which is just at the edge of at the edge of the case, which is going to just prevent the overlapping of aliases. So if we choose m to be equal to 12, it implies fs to be equal to 200 megahertz. So this example illustrates that we can choose sampling frequency which is much lower than the actual frequency content of the input signal which needs to be sampled. So it helps in designing an ADC which will consume less power because it's going to be operating at a much lower sampling rate. And even though 200 megahertz still can be higher sampling frequency for many applications, but it is a practical one. And once you have digitized this entire 100 megahertz band with the help of 200 megahertz sampling operation, we can do the further channel selection with the help of digital filtering. And just to complete the picture, the simple receiver which we are talking about has got a band select filter, then it has got a VGA, finally we have got an ADC, which is ADC, which is sampling the signal at fs as long as fs is meeting the above criteria. So this looks like very simple technique to digitize the input RF signal with the help of a ADC. But are there any drawbacks? To understand the practical challenges here, so from assuming that the sampling operation is all ideal, this is all going to make sense. But in reality, what happens is sampling operation requires you to, the most simplest form, implement a switch. In reality, what happens, you will be having not just a V in dash, you will be having a V in double dash, which is going to be the held sampled value, the input. So input voltage is first sampled, and once it is sampled, that voltage is stored across the capacitor, and this stored value, which is V in double dash, is later on quantized to convert into digital form. This is also called as sample and hold block. So even though the sampling frequency, as we have seen, can be much lower than the input frequency, okay, but if we want the sampling operation to be perfect, then this V in at the time of sampling has to be completely appear on the other side of the switch. And because of the non-ideality in these switches, this may not always be possible. And the simplest non-ideality which we can all think of is the switch having the on resistance. So now we are applying input voltage and we are trying to look at the sample and held value of this input voltage. We can see that this on resistance as well as there is a capacitor which is going to hold the voltage. Both of them are going to limit the rate at which input can change, because if the input is changing very fast, this node may not be able to follow the input signal, since it is having this extra this capacitance, along with that this internal resistance of the switch. So if I just show you the time domain behavior of this operation, it will become clear. Say this is the input signal, and we are trying to self with the help of clock signal to sample the input signal. So whenever this clock is here, okay, this is your clock. The clock signal. So every time this switch is turned on, this input voltage will try to appear at the V double dash node, and you can assume that this switch is turned on every time this clock signal goes high. So when the clock signal goes high, input tries to reach to the capacitor output, and at this instant when the switch is turned off, the value of Vn is going to get sampled across this sampling capacitor. So let us try to see how V in double dash looks like. V in double dash, initially let's say V in double dash was at 0. So when we turn on the switch, V in double dash will try to follow V in of t. So in reality, you want something like this. Something like this to happen. So let me show this as this is how ideally it should be. And every time we open the switch, so at this instant, switch is opened. And what happens? This value is going to be held till the next sample comes, okay, or till the next positive edge of the clock signal comes. And once that happens, this is going to again follow the input voltage. So on. Again, it is going to follow the input voltage. Okay, this is all fine. This is showing an ideal sampling operation. We are sampling the value of input at these instants, and these samples are going to exactly represent the value of V at those time instants. So in this figure, you can see during this phase, signal is going to track. So the V and double dash is going to track V, and then it is getting sampled. So this tracking phase, we can see as per our diagram, is during the positive half of the clock. So called as tracking. And once the signal has been tracked satisfactorily, at this instant, when we turn off the switch is turned off, signal is sampled. This is your sampling instant. So every negative edge of the clock is sampling instant. Okay. Once the signal has been sampled, during this duration, signal is held constant with the help of the sampling capacitor. This is also called as hold phase. And this tracking, sample, and hold, these phases are going to repeat every clock cycle. And we can see that as per this ideal sample and hold circuitry, the samples which are being held are true representation of the signal at the sampling instant. Now, in reality, because of finite resistance of the switch and this capacitance of the sampling node, there will be some kind of delay, or you can say some kind of low pass filtering when the switch is turned on from V into V in dash. So, as to understand this, let us try to see how a signal may look like in the presence of R on and C sample. Okay, so because of this R on and C sample, you will see some kind of delay. So this delay is going to make the signal which is getting sampled to be different than the input signal which has been applied. I may be showing a little bit exaggerated picture here, depending on the value of the R and C sample, you can see there will be some error here. Then the signal is going to be held, and when we reach the next starting phase of the tracking, this signal may not instantly jump to the input value because we have R on and C sample present in the circuit. There will be, from here itself, there will be some deviation, and then it will try to follow the input. And it may happen that again at the sampling instant, we will be capturing a signal which is not same as the input signal which we have applied. And this process is going to repeat. So there will be here, then we are trying to sample. Again, there will be difficulty in tracking the input. Okay. So this is in the presence of sampling capacitance. So if we are trying to design a circuit where signal needs to be sampled satisfactorily, we need to make sure effect of R on and C sample is minimal during the tracking phase. And this can be ensured if we make sure this low pass filter which is getting formed sample. So this low pass filter has a bandwidth which is much higher than the signal which is being applied. Another way to say this 1 by 2 pi R on C sample much higher than the maximum frequency of the input signal. And this parameter here is also called as tracking bandwidth. So we say that the tracking bandwidth has to be much higher than the maximum frequency of the input signal. Now we can see that even though it is possible to sample a high frequency signal at a much lower rate without losing information, this is also called as band pass sampling. But if the sample and hold circuitry is designed such that its tracking bandwidth is lower than the input signal frequency, then again we will not be able to sample the proper signals and will be losing information. So the conclusion is trying to digitize the signal directly with the help of ADC cannot be feasible, especially when we are talking about high frequency signal being received. Okay. The reason is even though sampling frequency can be lower, but the tracking bandwidth has to be much higher. And this tracking bandwidth the maximum signal frequency which can be sampled. So you can see that the tracking bandwidth is getting limited by this property of the switch itself. And even though there is no separate sampling cap added in the circuitry, the switch itself may have its inherent parasitic capacitance. So this product R on into C parasitics of the switch is going to directly limit what is going to be the tracking bandwidth in a given technology. C of product of switch in a given technology. Okay. So now let us look at another approach which doesn't require the ADC to have such a high tracking bandwidth.